remember that in our previous discussion of calorimetry, the previous problem that we worked, we looked at how to relate the amount of heat or quantitate the amount of heat that's required to cause a substance to increase or decrease in temperature. And so what we want to do is we want to be able to put this together with not only how much heat does it take to increase water from 20 degrees to 80 degrees C, but we also want to start looking about a more holistic picture of thermodynamics, as in, if we're adding heat to that substance, where is that heat coming from, and what type of change does that other substance undergo? And so what I really mean by that is this idea that heat flowing from one place to another, and we talk about in that previous problem, the water, and its temperature increasing from 20 degrees to 80 degrees C. That is our system that we're studying, that water. And so we are looking at that particular part of the universe, and everything else would be considered the surroundings. So the heat that's required to increase that particular beaker of water or container of water would be coming from the surroundings. And so we want to start looking at and thinking about this heat transfer and where that heat comes from and goes to. So this type of problem, or this problem, deals with a beaker of water with 600 grams of water in it. And that water is at 25 degrees C. Then we have a 55-gram piece of iron that we've heated up to 425 degrees C, and we're going to dump it into that beaker. So we've got cold water, we've got a hot piece of iron, we're going to put those two things together. What's going to happen? Well, as you might expect, if you put something hot into some cold water, the water is going to heat up. And as you might expect, if you put something hot into some cold water, the hot thing is going to cool down, so the iron would cool down. Now, we know how to handle that in terms of heat equals mass times specific heat times change in temperature. We know that equation already. We know what is involved in using it. And so we want to put the two things together for the two substances, for the iron and for the water. And so I'm going to write an expression up here that we're going to use that's going to govern all of our calorimetry problems, advanced calorimetry problems. And it's going to be the amount of heat that's lost plus the amount of heat that's gained is equal to 0. Now in your textbook, or you will see in lab, if you're doing calorimetry in lab, a lot of times you'll see this written as heat lost equals negative heat gained, or something like that. This and that are exactly the same expression, but for me, this is easier for me to understand. Okay, easier for me to conceptualize or remember, is that heat lost plus heat gained equals 0. In other words, the amount of heat that is being lost and the amount of heat that's being gained have to be equal and opposite in sign, such that those two things would cancel out, and so the change in energy for the universe would equal 0. In other words, the law of conservation of energy would be obeyed. That's exactly what this expression is all about. So in this problem, we have something losing heat and something gaining heat. What's losing heat? Well, you can simply ask the question, what is cooling down? Well, the thing that's cooling down would be the thing that's losing heat. That's the iron. And the thing that's gaining heat will be the thing that's increasing in temperature, and that's going to be the water. Because we're going to add something hot to the cold water, its temperature is going to increase. The water's temperature is going to increase, the iron's temperature will go down because of the influence of the water on the iron. So we can write an expression, mass times specific heat times change in temperature, for each of those two situations, for the iron and for the water. So mass, specific heat, change in temperature for the iron, plus mass, specific heat, change in temperature for the water, and those two have to add up to be 0. So you're going to see that in reality, the hard part about this problem is really going to be figuring out what goes where. And we have to be very particular about our change in temperature. Remember we said a change in temperature is always equal to the final temperature minus the initial temperature. So it's going to be very, very important that we maintain that, that convention the entire way through. You may be in physics or you may be in some other discipline where you will find that they calculate those changes differently. That's okay. It works the same way mathematically, except their definition of change in temperature will be different. But in chemistry, we always do final minus initial. So let's start trying to plug some things in. You're going to see that a lot of dominoes are sort of going to fall, and we're going to end up with one thing that we have to solve for. Now, once we have that, if you're strong in algebra, it's not going to be a real problem to solve this. But I will say that the algebra, the amount of algebra that goes into this, not the difficulty so much as the amount, is there's going to be a lot of it. So let's look at the iron first. And we take a look at the iron and we say, what's the mass of that iron? Well, it's a 55 gram chunk of iron. And the specific heat? Well, the specific heat is given as 0.451. And that's joules per gram degree C. Now, the way that I know that I need the mass, instead of the number of moles, remember we've talked about the idea of a molar heat capacity, or if we haven't, there is something called a molar heat capacity where the units are joules per mole degree C, in which case you would put moles here instead of grams. The only difference is the unit that we see on our heat capacity. So if you want to know how to handle that, always look at your heat capacity first, and you'll know whether you need grams or you would need moles here. Other than that, there's no difference in how the equations will function. Now, our change in temperature, and all of this is going to be for iron, so I'm going to end up putting it all in brackets. So my change in temperature is going to be final minus the initial. So the final temperature of both the water and the piece of iron when it comes to thermal equilibrium is what we're trying to calculate. We don't know what the final temperature is. But we do know that the iron and the water will end up at the same temperature. That's why we call it thermal equilibrium. So we've got our final temperature. We just need to subtract from that the initial temperature of the iron, and that's 425 degrees C. And all of that business right there has to do with the iron. And from that, we're going to add the same information for the water. So for instance, we start off with 600 grams of water in our beaker. And we know the heat capacity of water is 4.184 joules per gram degree C. Again, the grams here in the specific heat capacity will tell me that I need to have grams here in this equation as opposed to moles. And lastly, change in temperature. Well, we know the final temperature of the water is going to be the same as the final temperature of the iron. We don't know what that final temperature is yet, but we do know that we started at 25 degrees C. And all of that business right there is going to be the water. So you add those two things up, and they're going to equal 0. All right, now here is sort of the challenging part for a lot of students. It is taking this expression and solving it for the final temperature. In reality, there is not a lot beyond basic algebra here. It's just collecting terms, simplifying terms, collecting like terms together. However, it is a real challenge for a lot of students to do a problem like this algebraically. There's just a lot to it. So what I'm going to do is, instead of doing the problem for you right now, what I'm going to do is I'm going to say, okay, let's take a 5-minute break. You go, you try to solve this mathematical expression, right? Once you do that, just go ahead and pause the video right here. I'll actually have a black screen that will come up in the video. You can pause it. And then come back, and I will have the problem worked out on the board, and I can talk about what I've done to work through the different steps to show you what I've done to solve it. Okay? So pause it, try to solve this for the final temperature, and then come back, start the video again, and I will give you an idea of what the answer will be. Okay, so let's cut right to the chase. All right, what's the answer to the problem? Well, you should be able to solve it and you get a final temperature of 28.9 degrees C or somewhere around there. Rounded to the correct number of significant figures should be 29 degrees C. It's a challenging problem to work through with significant figures. There's a lot to it, but you should end up with those two at the very end, so 29 degrees C. So that means you put this really hot piece of iron into this cold water, and even though there's a small amount of iron, it can heat the temperature of the water up considerably. You might not think that 4 degrees is considerable, but in reality, it actually is a significant amount of heat that's being transferred to the water. But at the same time, it didn't increase it to boiling temperature or anything like that. And that's probably or mostly because the heat capacity for water is so high. It will suck up a lot of heat before its temperature will change. We talked about that a little in class when we talked about heat capacity. But now if you needed some help solving it, you didn't get that answer, how did I work through the problem? Well, I just recopied everything right here on the top. Next part, I have gone through and I have multiplied the 55 times the 0.451 and the 600 times the 4.184. That's all I did. I just did the multiplication part in that first part. Kept everything in brackets just because I wanted to keep it all separate. My temperature final is still here, still in the same place. So you can still find it. We still have the final minus initial temperatures there. But my next step is now I have this number times this expression here in parentheses, and I've got to distribute that. And when I do that, I got to multiply it by the temperature final, and I've got to multiply it by that initial temperature. And so I get two completely different terms from those three that I started with. My T final is here. I get actually a 24.805 T final minus 10,542. And then I'm going to do the same thing for the water. I mean, 2,500 and 10.4 times temperature final minus 62,760. Now, this is no different than if you have 2x plus 3x plus 5 equals 0. I'm going to collect all of my terms that have variables. As long as the variables are the same, I can add them together, and I do that. So I get 2,535.205 times temperature final. Collected all those temperatures together. I can also collect all of my numbers together, things that don't have any variables. And I do that to get minus 73,302. All right. Next step, well, what I want to do is I want to get all the numbers on one side, all the variables on the other, so then I can solve for the answer, solve for the value of that particular variable by dividing. So I'm going to add 73,302.125 to both sides. So it gets rid of it on the left-hand side, and it ends up on the right-hand side as a positive number. Now, one way to know that you're doing a problem like this correct is that, remember, what we're expecting is that the final temperature, okay, is going to be greater than 25 degrees C. And so we're going to expect that to be some positive temperature, not negative. So if this had come out as a negative, right there should be a sign to you that the way I'm working this is not correct. Now, one other way that this problem can be solved is if they would give you all of the temperatures but not give you the specific heat capacity of one of your particular components that you're using to perform this experiment or this calculation. In which case, those specific heat capacities, whether they're molar or whether they're in terms of grams, they always will work out to be a positive number. They're never going to be negative. So that's another sign if you're working the problem that way and this comes out to be negative, you know you've done something wrong. Okay, so Now we've got some number times TF equals this 73,000, and I'm just going to divide both sides by that 2,535.205. Crosses out here, so I get T final by itself, and then I end up with my temperature on the right-hand side. Then I just round it to the correct number of significant figures. I get my 29 degrees C. In reality, I'm going to tell you that students struggle with calorimetry, not necessarily because they can't get this part. A lot of students can get that. I mean, I seem to be able to teach students to be able to get the expression right. But going from there has been a real struggle over the last few years. If you find that you can't solve this problem, try to solve it again now that you've seen me work through it. Turn off your computer or turn away from it. Try to work the problem again, see if you can get it. If you can't, please come to see me. We can talk about some tricks or some tips on how to perform an algebraic manipulation like this. But that's calorimetry.